Okay, rotational motions. So we have the omega, final angular speed, expressed in region per second. Omega sub zero, initial angular speed. We have the alpha here, the angular accelerations. We have the theta, the final angular displacement, and the initial angular displacement is theta sub zero. So this is our equation. So we have an example of this, an angular displacement with constant acceleration. So the problem here is a rotating wheel starts at an angle of zero with an initial velocity of 2 regions per second, and it accelerates with angular acceleration of 3 regions per second squared or time interval 4 seconds. Find the angular displacement. So by substitution here, the initial angular displacement is equal to zero. And the initial angular uh, speed is equal to 2. And the time here is equal to 4 seconds, the time interval. Then here we have the uh, acceleration equal to 3 regions per second squared. And the time here is equal to 4 seconds squared. So that is equal to 32 regions. So here is the answer. Okay, the angular speed with constant accelerations. The spinning fan, a fan starts from rest, angular sub zero equal to zero, and accelerates at 2 regions per second squared for the time interval equal to 5 seconds. Find the angular speed after 5 seconds. So by substitution here, this is the angular speed initial, this is equal to zero. Then we have here the angular acceleration equal to 2 regions per second squared. And we have here 5, the time interval. So this is equal to 10 regions per second. So the answer is the angular speed is 10 regions per second. Okay, the next problem is about the angular motion without angular motions without time. So we have a spinning disk here. The initial angular speed is equal to 5 regions per second. The angular acceleration is 2 regions per second squared. The displacement, the change in displacement is 10 regions. So this is angular displacement, 10 radians. Okay, because the uh, initial displacement is equal to zero here. Okay, so find the angular speed. So this is the angular speed. So we substitute here. This is the angular uh, speed, 5 regions per second. So the two here is equal to 2. Then we have the angular displacement, angular acceleration. The angular acceleration is 2 regions per second squared, and the time interval here. And the change in displacement is equal to change in angular displacement is equal to 10 radians. So this is equal to 65. So the final angular speed is square root of 65. That is approximately equal to 8.06 radians per second squared. So we have the torque here. A torque is the rotational equivalent of force. Everyday life experience or everyday life examples. Opening a door. A torque is applied when you push on the edge of a door to make it rotate on its hinges. Using a wrench, turning a bolt involves a torque. Force applied at a distance from the bolt, a distance center, causes rotation. So turning a steering wheel Your hands apply a force on opposite sides of the wheel, creating a torque to steer the car. Seesaw or teeter totter. When one side is pushed down, a torque is created about the pivot point in the center. Pedaling a bicycle, you apply a force to the pedal, and because it offsets from the crank center, it creates a torque. Physics and engineering examples, turning on a rotating desk. In physics problems, a constant force applied tangentially at a radius from the axis of desk produces a torque equal to R times F. All right, so we have the electric motor. So we have example here, a torque is produced in the motor when magnetic field interacts with the current in the motor. So we have here the rotor inside, we have this stator uh, around this rotor. Torque on a beam. A force applied at one end of a horizontal beam causes a torque about the point where it is fixed. Torque in the planetary motion. Gravitational torque can affect the rotation of celestial bodies. For example, a tidal torque slowing Earth's rotations. So we have the high tide and low tide here. So it affects the rotation of celestial bodies. Gyroscope torque in spinning wheels or gyroscope. The angular momentum changes direction due to external torque. So we have example here where the torque here equals to RF sine of the angle. So where the tau here is the torque in Newton's meters, R is the distance from pivot meters, F is the applied force. We have the angle here between the force and the lever arm. Opening a door, no? So force is 30 newtons. Distance from the hinge is 0.9 meter. The angle is 90 degrees, force perpendicular to a door. So the torque here is 0.9 times 30 times sine 90 degrees, equal to 27 Newton meter. So using a wrench, so a force is 50 newtons, length of wrench is 0.25 meter. Angle between the force and the lever arm length is 30 degrees. So the torque here is 0.25 times 50 times sine 30 degrees, equal to 6.25 Newton meter. Pedaling a bicycle, force on the pedal 100 newtons, crank length 0.17 meter, the angle is 90 degrees. A torque is 0.17 times 100. Because sine 90 degrees is equal to 1, so that is 17 Newton meter. Torque on a rotating beam. Force 100, 200 Newton downward. Distance from pivot is 1.5 meter. So the angle is 45 degrees to the beam. So that is 1.5 times 200 times sine 45 degrees equal to 212.1 Newton meter. A rotational analog of Newton's second law, a torque is equal to the moment of inertia times the angular acceleration. So we have here a torque, tau, and L, and I here is the moment of inertia, and we have here the angular acceleration. Spinning a solid disk, you apply a torque to a solid disk like a flywheel to make it spin faster. So the mass of disk is 4.0 kilogram. The radius is 0.3 meter. The angular acceleration is 2.5 radians per second squared. First, compute the moment of inertia for a solid disk. So here's the formula for the inertia. We have the common moments of inertia here. So you can use this formula. Now apply the rotational flow here. So moment of inertia times the angular acceleration is 2.5. 2.5. So 0.18 times 2.5. This is the moment of inertia, 0.18. So that's equal to 0.45 Newton meter. Okay, the kinetic energy, rotational kinetic energy due to angular velocity. So given by this equation, one half of the moment of inertia times square of the angular speed. So we have rotational kinetic energy, and here is the moment of inertia, and we have the omega, the angular velocity. So rotating solid disk, a solid disk of mass 5 kilogram and radius 0.4 meter spins at 10 radians per second. What is the rotational kinetic energy? So the moment of inertia of a solid is 1/2 mr squared, uh, 1/2 of 5 times 0.4 squared. So our radius here is equal to what? Given radius here is zero point 0.4. So the mass is 5 kilograms. Okay, so plug into the kinetic energy formula. So 1/2 times 0.4 times 10. So that is equal to uh, 20 joules. So the rotational kinetic energy of the disk is 20 joules. Gravitation. So we have the gravitational force between two masses. So F here is the gravitational force in newtons. We have the gravitational constant 6.674 times 10 to the negative 11 Newton meter squared over kilogram. In 1 and M2, we have the masses of the objects in kilogram. R is the distance between their centers in meters. Gravitational force between Earth and uh, this is 1 and 70 kilogram. Uh, 70 kilogram person. So the mass of Earth is 5.972 times 10 to the 24 kilogram. Mass of person is 70 kilograms. Radius of Earth, distance from the center is 6.371 times 10 to the 6 meter. So by substitution here, so by using this formula here, so we have 607 Newton. So the gravitational force between Earth uh, and 70 kilogram person is approximately 687 Newton, which matches their weight. Compute the gravitational force between the Earth and the Moon using the same formula. So mass of Earth is 5.972 times 10 to the 24 kilogram. Mass of Moon is 7.348 times 10 to the 22 kilogram. This the distance between Earth and Moon, 3.844 times 10 to the 8 meter. Gravitational constant, 6.674 times 10 to the negative 11 Newton meter squared over kilogram. So by substitution here, this formula, we have 1.982 times to the 20 Newton. So the gravitational force between the Earth and the Moon is approximately 1.982 times 10 to the 20 Newton. So we have the third one, the gravitational potential energy between two masses. The negative sign here indicates that the potential energy is zero at the infinite separation, and negative when the objects attract each other. Gravitational potential energy between Earth and Moon, let us use the same value as before. So M1 is the mass of the Earth, 5.972 times 10 to the 24th. And mass 2 is the mass of the Moon, 7.348 times 10 to the 22 kilogram. The distance between the Earth and the Moon is 3.844 times 10 to the 10. Remember that is the distance between their centers. So by substitution here, the answer is negative 7.62 times 10 to the 28 joules. So the gravitational potential energy between the Earth and the Moon is approximately negative 7.62 times to the 28. Gravitational potential energy between two people. So imagine Person A has mass 70 kilograms. Person B has mass 60 kilograms. Distance between them is 1.0 meter. So using the formula and by substitution, we have U equal negative 2.802 times 10 to the negative 7 joule. The gravitational potential energy between the two people, as expected, it is very small value because the gravitational force between small masses is weak. Right. So we have the gravitational speed of a satellite in circular orbit. So we have the equation here. The formula to use is the square root of the the product of the gravitational constant and the mass of the Earth over the uh, R here is the distance from the center of the massive body to the orbiting object. Okay. The speed of a satellite orbiting the Earth at 400 kilometers altitude. So the mass of the Earth here is 5.972 times to the 24 kilogram. The radius of Earth is 6.371 times 10 to the 6 meter. Altitude of satellite 300 kilometers equal to 3 times 10 to the 5th meter. So R here is the radius of the Earth plus the altitude of the satellite. So 6.371 times 10 to the 6 plus 3.0 times 10 to the 5. That is 6.671 times 10 to the 6 meter. So by substitution here, the satellite speed is 7,730 meters per second. So we have the skip speed from the planet's gravity. It is the minimum speed now needed for an object to skip the gravitational pull of a massive body without further propulsion. So we have the skip speed velocity. We have m here, the mass of the planet or celestial body. R is the distance from the center of the planet to the object. So the skip velocity from the surface of the Earth. So the mass of the Earth is 5.972 times 10 to 24 kilogram. The radius of Earth is 6.371 times 10 to the 6 meter. By substitution in the formula, we have the square root of 2 gm. So that is 11,186 kilometer per second. The approximate escape velocity from the Earth's surface. Simple harmonic motion. So given by this one, this is what we call the displacement in oscillatory motions. So we have here x of t displacement at time t in meters. And we have capital letter E, the amplitude maximum displacement. We have the omega, the angular frequency. This is equal to 2 pi f. If here is the frequency in region per second. And we have the phase constant and the time intervals. The mass on the spring. So let's say the amplitude of the spring is 0.1 meter, 10 centimeter. The angular frequency is 2 pi radians per second. Okay. Then the phase angle is pi over 4 radian. We want to find the displacement after 0.5 seconds. So by substitution here, so we have 4 pi. This is equal to the angular frequency times 0.5 here. 0.5 is the time interval. Using this formula here, so evaluating, we have 0.0707. So a time equal to 0.5. The object is approximately 7.07 centimeter from the equilibrium positions. The angular frequency of mass spring. K is the spring constant. M is the mass attached to the spring. And we have the omega, the angular frequency in radians. Suppose the spring constant is 200 Newton per meter. The mass of the object is 2 kilogram. So the angular frequency is equal to 10 radians per second. This is the angular frequency of the mass spring system is 10 radians per second. The period T of a spring oscillator. So M is the mass attached to the spring. K is the spring constant. So period of a spring mass system, mass M equal to 0.5 kilogram. The spring constant is 20 Newton per meter. So by using this formula, the period of the spring mass system is approximately 0.993 seconds. Okay. The period of a simple pendulum of length L, simple pendulum, suppose the length of the pendulum is 1.0 meter. Acceleration to gravity is 9.8. So by substitution here, we have 2 pi. So L is equal to 1.0, the length of the pendulum, and over 9.8, the acceleration due to gravity. This is approximately 2.00 seconds. So the period of a 1 meter pendulum on Earth is approximately 2.00 seconds.